Okay, today in this video we're going to talk about something called sequences, and sequences are very different than anything that we've studied all year long. And in its simplest sense, a sequence is nothing more than an ordered progression of numbers. It's a list of numbers. So you've been dealing with sequences for a very long time. 1, 2, 3, 4, 5 is a sequence. 1, 3, 5, 7, 9 is an odd number sequence. 2, 4, 6, 8, 10 is an even number sequence. 1, 4, 9, 16, 25. Those are perfect squares. I'm just squaring numbers. And so that's a sequence. And that's what we're going to talk about in this video. Now, there are two ways to define a sequence. One is called explicit, and the other is recursive. And so in this first example, we're going to talk about an explicit sequence. Now, an explicit sequence is a sequence that you generate the sequence by plugging in the term number. So let's just say, it says here in this first example, find the first 6 terms and the 100th term of the sequence in which a of k is equal to k squared minus 1. So if I'm looking for the first number in this list, or the first term in this list, I would call that A1. And I would plug in 1 for k. 1 squared is 1 minus 1 is 0. And then A2 would simply be 2 squared, which is 4 minus 1, which is 3. And A3 is going to be 3 squared, which is 9 minus 1 is 8. And then you can see where this is going. This is pretty simple stuff. A4 is going to be 15. A5 is going to be 24. And A6 is going to be 35. 6 squared is 36 minus 1, so that's 35. All right, so if we want to find the 100th term, no problem, then we would just say A100, and that is equal to 100 times 100 is going to be 10,000 minus 1, so that's going to be 9,999. All right, and so essentially that's all an explicit sequence is. It's nothing more than generating the list of numbers by plugging in the term number that you're looking for. Okay, we said on the first slide that there are two ways to define a sequence. The first was an explicit sequence, and once again, let's refresh that an explicit sequence is a sequence that you generate the terms by plugging in the term number. So if you want the 50th term, plug in 50. If you want the 100th term, plug in 100. But now we're going to talk about something called defining a sequence recursively. Now note, let's read this. This simply means using the previous term to derive the next term. This can be kind of confusing sometimes for students, so we want to take this slow. Essentially, what we're basically saying is that if you want to get the 7th term in a list of terms, you need the 6th term. If you want to get the 100th term, you will need the 99th term. So the term that you're looking for is based on or is dependent upon the term that came immediately before it. So let's see if we can figure this out. It says find the first 6 terms and the 100th term for the sequence defined recursively by the following conditions. So it's giving you the first term. B1 is 3. Now we need to find B2, B3, B4, B5, B6. So B2, all right, now let's just look at this. It tells you B sub n is equal to B sub n minus 1 plus 2. Now, let's just interpret this. This is saying that the nth term is equal to the n minus 1 term, which is the term that came right before the nth term, plus 2. So if I'm looking for B2, I just simply need B2 minus 1, or that's equal to, actually let me just put it here, plus 2. We know 2 minus 1 is 1, so we're looking for B1 plus 2. Oh, they gave me B1. B1 is 3. Hey, 3 plus 2 is 5. Now we've got the second term. Now we're going to move on to the third term. And guess what? The third term is dependent upon, well, let's just plug it in. B3 is equal to B3 minus 1. B3 minus 1 plus 2. All right, we know 3 minus 1 is 2, so B2 plus 2. Oh, we just got B2 right here. B2 is 5. So guess what? We can plug 5 right in there, and 5 plus 2 is 7. I think you see where this is going. So what is the pattern? If you want the fourth term, you take the term that came before it and add 2. So it doesn't take a mental giant to figure out where this is going. 5, 7, 9, and then B5 is going to be 11, and then B6 is going to be the previous term plus 2. That's going to be 13. All right, so now we can see what the list of numbers is. It's simply going to be 5, 7, 9, 11, 13. All right, now notice that we're looking for the 100th term. Now clearly we do not want to carry this pattern all the way out to the 99th term so that we can get the 100th term. So what you can do in situations like this is you can recognize this as a as a sequence, and you can write a little formula that will give the explicit formula for this. So let's just see if we can do that. All right, so if we come up with, let's say, this formula, b sub n is equal to 2n plus 1. Now notice this is an explicit formula because in order to get the nth term, you have to plug in the term number. Notice it's not dependent upon a previous term like this formula is. So I just generated this. I recognize this to be this list that we have here is the odd numbers, 3, 5, 7, 9, 11, 13. And this is the general formula for the odd numbers. You can check it if you want. When n is 1, 2 times 1 is 2, plus 1 is 3, check. When n is 2, 2 times 2 is 4, plus 1, that's 5, check. When n is 3, 2 times 3 is 6, plus 1, that's 7, check, and so on and so forth. So if I'm looking for the 100th term, all I do is take 2 times 100 plus 1, and that is going to give me 201. And so there is the 100th term. Okay, now we're going to talk about something called converging and diverging. And a sequence converges. Let's talk a little bit about this. A sequence converges if the list of numbers heads towards a finite number. So if the list of numbers is heading towards a finite number, then we say that it converges to that number. Now, if a sequence diverges, then one of two things is happening. Either A, the sequence is heading towards an infinite number, or it's heading towards infinity, or the sequence is oscillating back and forth. I'm not going to try to finish that. Oscillating back and forth between two fixed numbers. And so we really can't determine what the list is heading towards because it keeps oscillating back and forth. A good example of this would be a sine curve that we studied in trigonometry. You see it goes up to 1 and down to -1 and up to 1 and down to -1 and up to 1 and down to -1. And it never really levels out. It just keeps going back and forth. Then that is an example of something that is going to diverge the bigger that n gets. So that's the idea here. And so now what we want to do is we want to figure out whether these sequences converge or diverge. And really, for a lot of these, we can use the idea that we learned earlier in the year, which is the Bobo, Bosco, and Botno idea. And that's simply, these are just acronyms that help us figure out the horizontal asymptote, or we may want to write it this way, since many of you are going to be taking calculus next year. The limit as n approaches infinity of the function a sub n. In other words, let me break that down. What we're asking is, what is the list of numbers heading towards if we let the term number head towards infinity? And usually by doing that, you can figure out what the list of numbers is heading towards. So for instance, let's look at this. You have a list 1 over 1, 1 over 2, 1 over 3, 1 over 4. Well, the top is just fixed to be 1, and the bottom keeps going up each time. The bottom is the term number. The first term number is 1, second term 2, 3, 4. So we can take this list and we can write a little formula for it. Oh, this must be 1 over n. All right, and so now we can ask the question, as n approaches infinity, what is 1 over n doing? Well, there's a couple ways to look at this. Well, we know the graph of 1 over n looks like this. This is a rational function, reciprocal function. So as the x-axis goes towards infinity, the y value is heading towards 0. We could also look at it as Bobo. When the power is bigger on the bottom, it's going to head towards 0. We can also just look at the numbers pretty simply and say, oh, okay, the top is going to be 1. The bottom keeps getting bigger and bigger and bigger and bigger and bigger. So 1 over a really big number is heading towards 0. So if it converges, you want to tell us what number it converges to. So for instance, in letter A, you would say that this converges to 0. All right, let's take a look at letter B. So we have 2 over 1, 3 over 2, 4 over 3, 5 over 4. Notice it does not give us the formula, but we can figure it out. Notice that the top is always 1 more than the bottom. And the bottom is simply the term number, 1, 2, 3, 4. So in other words, the first term in this list has 1 on the bottom. The second term in this list has 2 on the bottom. So we know the bottom must be just simply n. Oh, the top is 1 more than the bottom, so the top must be n plus 1. Now, we need to figure out what this is going to do. So if we say the limit as n approaches infinity, in other words, if we let this list of numbers go way, 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 way out, what is it going to converge to? Well, a good thing to do if you have time is to just plug in some numbers in the calculator. 2 over 1 is 2. All right, so let's just write it out. 2 over 1 is 2. 3 over 2 is 1.5. 4 over 3 is 1.33. 5 over 4 is 1.25. Do you see what's happening? The numbers are heading down, and they're eventually going to level off to something close to 1. Oh, but how did we get that? Well, because if you remember Bosco, when the powers are the same on the top and bottom, which they are, end of the first, then you use the coefficients in front. 1 over 1 is 1, so you can say that this is going to converge to 1. It's going to converge to 1. So that's what you'll write for this one. Converges to 1. Okay, letter C. 2, 4, 6, 8, 10. And that's pretty obvious. The numbers are getting bigger and bigger and bigger, and the longer the list goes, the numbers are heading towards infinity, which means it's going to be diverging. It's going to be in this category here. So therefore, you'll say it diverges. And if it diverges, you don't say what it diverges to. You just say it diverges. Okay, look at the letter D. You see that the numbers are oscillating, -1, +1, -1, +1. We don't know what this is doing. It keeps going back and forth. So that's going to be in this category over here, an oscillation. So therefore, this is also going to diverge as well. All right, we're going to practice what we learned in example 3, and we're going to determine whether the sequence converges or diverges. If it converges, give the limit. So once again, what we are asking here is if we were to write out a whole bunch of terms, are the terms headed towards a finite number or are they heading towards a really big number? So what we're going to do is we're going to take the limit. Let's actually get a pen. We're going to take the limit as n approaches infinity, or as the term number gets bigger and bigger. We're going to see what this function goes to. Well, once again, we can see that the power on the top is 1 and the power on the bottom is also 1. So the powers are the same. When that is true, we look at the coefficients, 3 over 1, and so that is going to be 3. So this is going to converge to 3. Now, once again, if you were to graph this, then you would see that the horizontal asymptote would be somewhere around, it would be y equals 3. So the numbers are heading towards 3. Okay, let's look at letter B. Here we have a situation where the power on the bottom is bigger than the power on the top. So you remember that's the Bobo. When the power is bigger on the bottom, it's going to be going to 0. So hey, there's our answer right there. This is going to converge. Oops. It's going to converge to 0. All right, letter C. Oh, now we have a power that's bigger on the top than we do on the bottom. So maybe we'll call this Bosco over here, and we'll call this Bobo. And now we have Botno, where the power is bigger on the top. There's no horizontal asymptote. And this is just common sense. Think about it. If you're cubing a number on the top and you're squaring a number on the bottom, then the top is always going to be way bigger than the bottom, which means the numbers are eventually going to head towards infinity. So it's going to head towards infinity. So if that is true, therefore, this is going to diverge. Okay, in the next couple examples, we're going to talk about two different types of sequences. One is an arithmetic sequence, and the second is a geometric sequence. And this is a very simple concept. An arithmetic sequence is a sequence of numbers whereby you add the same number each time to get the next number. All right, so you add the same number to the previous term to get the next term. So we have, for instance, -6, -2, 2, 6, 10. We're adding 4 each time. 2 plus 4 is 6, 6 plus 4 is 10, -2 plus 4 is 2, so on and so forth. And so the basic equation that we want to use here is a sub n is equal to the first term plus n minus 1 d. And that is the idea. All right, so we're going to first letter A. So for number 1, we're going to do A, B, and C, and D. So letter A, what is the common difference? That is what the letter D stands for. It is 4. So you're adding 4 each time. That's the difference. All right, B, what is the 10th term? Well, tell you what, we're going to go out of order here. We're going to write an explicit rule for the nth term, and then that way we'll just be able to plug in 10 into that. So we're going to use our little formula, A sub n. So actually, let's make this letter D. So A sub n is equal to the first term in my list. That's -6 plus n minus 1. Just leave that there. And D is the difference. So that's going to be 4. All right. So we can leave it that way, or better than that is to distribute the 4n. So that's going to be 4n, let's see, -6, and then 4n minus 4. So that's going to be 4n minus 10. There we go. That's easy. So now we can get B, which says what's the 10th term? So A sub 10 is going to be 4, and then we'll plug 10 right in there. So that's 4 times 10 minus 10. That's 40 minus 10. That's 30. So if we were to continue this list out, let's just see. All right, this is term 1, 2, 3, 4, 5. And then if I add 4, that's going to be 14. That's 6. Add 4 more, that's 18. That's 7. Add 4 more, that's 22. That's 8. Add 4 more, that's 26. That's 9. Add 4 more, that's 30. That's 10. So once again, this just gets you directly to the answer. So that's going to be 30. And then we have the explicit rule, the recursive rule, part C. And so part C is we need to say that, once again, that the term we're looking for, A sub n, and this is real easy, is equal to the previous term plus 4. It's pretty simple. The previous term plus 4. And once again, you can see this. If I'm looking for the 10th term, I would take the 9th term, the previous term, and just add 4 to that. If I'm looking for the 8th term, I would take the 7th term and add 4 to that. All right? We're going to skip part 2 of example 5 for now. We'll come back to that later. Okay, in the previous slide, we talked about an arithmetic sequence, and now we're going to switch gears and talk about a geometric sequence. And a geometric sequence, once again, is a sequence that you get the list of numbers by multiplying the previous term by some number. All right, and it's going to be the same number you're multiplying. So let's say an example would be 1, let's say 1, comma 4. Now what did I do with 1? I multiplied 4 by it to get 4. And then I multiply 4 and I get 16. And then I multiply 16 by 4 and I get 64. And I multiply 4 times 64 and I get 256, and on and on. I'm just taking a number and multiplying it by 4. that is a geometric sequence. If I'm adding the same number, that's an arithmetic sequence. So the formula, once again, is a sub n, and it's going to be the first term times r, and r is what you're multiplying by, to the n minus 1. All right, so let's see if we can do this. Here we have 3, 6, 12, 24, 48. Very simple. What is the common ratio? Letter A. What, in other words, what are you multiplying by each time? Well, you're clearly doubling your numbers, so the ratio r equals 2. 3 times 2 is 6, times 2 is 12, times 2, so on and so forth. All right, so now we're going to jump down and do letter D, which is the explicit rule. And we're going to use this guy right here. So a sub n is equal to the first term, which is 3, parentheses, r, we just found that. It's going to be 2 to the n minus 1. All right, let's test out a few and see if this is true. A1 is going to be 3 times 2 to the 1 minus 1, which is 0. 2 to the 0 is 1. Anything to the 0 power is 1 times 3 is 3. All right, let's plug another one in. Let's say A4. All right, 3 times 2 to the 4 minus 1, that's 3. 2 to the third is 8 times 3 is 24. All right, bingo and bingo. That is the idea. So now let's go to letter B. And it says we need to find the 10th term. So we can do that. So A sub 10 is simply going to be 3. And then 2 to the 10 minus 1, 2 to the 9th. And let's see what that would be. 2 to the 5th is 32. To the 6th is 64. To the 7th is 128. To the 8th is 256. So 512 would be 2 to the 9th times 3. So whatever 512 times 3 is, that's going to be 1536. And that is the 10th term. Okay, now we're going to go to part C, the recursive rule. And I think this is pretty clear. The recursive rule simply says if you're looking for the nth term, hey, take the term that came before it, an minus 1, and multiply it times r. So a sub n is simply going to be an minus 1 times r. And in our problem, r is 2. So there it is. So once again, let's just test this out to make sure you're comfortable. If I'm looking for a5, I would say a5 minus 1 times 2. 5 minus 1 is 4, so I would take a look at the fourth term and multiply it by 2. So let me see, 1, 2, 3, 4. The fourth term is 24, so that would be 24 times 2, 48. So in other words, if I want the fifth term, I would need to know what the fourth term is. All right, we're going to put it all together in this last example here. And it says the second and fifth terms of a sequence are 3 and 24, respectively. Find the explicit and recursive formulas for the sequence if, first of all, it's arithmetic and then geometric. So over here, we're going to do the arithmetic example. Now, once again, what does that mean? That means that we are assuming that from 3 to 24, you're going to be adding the same number each time to get from the second term to the fifth term. And then over here, we're going to assume that it is geometric, which means from 3, the second term, to 24, the fifth term, we're going to have to multiply by the same number to get to 24. All right, so let's assume that this is arithmetic. So if we remember from the last slide that the formula that we learned is a sub n is equal to a1 plus n minus 1 times d. So we know that the second term is 3. So we can write that down. a2 is 3. a5 is 24. So let's go ahead and plug that in. a2, let's just write it out. a2 is equal to a1 plus 2 minus 1, because n is 2 in this particular situation. So 2 minus 1 is 1 times d. Oh, we already know a2. a2 is 3. So we can basically say what? 3 equals a1 plus D. All right, so let's also do A5, which is going to be 24 equals A1 plus 5 minus 1, which is 4D. All right, now notice we have two equations with two variables. We can go back to Algebra 1 and we can use substitution or we can do elimination. Let's just go ahead and do elimination. So let's say we're going to subtract the top minus the bottom. All right, we could do it either way. We could put the top on the bottom, whatever. But 3 minus 24 is negative 21. Oh, A1 minus A1, that's how it is eliminated. That's why it's called elimination method. And then we have 1D minus 4D. That's going to be negative 3D. Divide by negative 3. You see where this is going. So D is 7. Okay, so if we take 7 and plug it back into here, then we get 3 equals A1 plus 7. Subtract 7. And voila, A1 is negative 4. So now that we know all of that, now we can write our little formula. See if we have space for it. Actually, we're probably going to need to erase some things. So let's erase all of this so we can make room for our formula. So this is going to be, now that we know that, oh, we erased everything. We know that D is 7. We know A1 is negative 4, so we'll say A sub n is equal to negative 4 plus n minus 1 times 7. And then to make it look really nice, we're going to distribute. So that's going to be negative 4 plus 7n minus 7. And so that's going to be 7n minus 11 is equal to A sub n. So this is our formula. All right. So now that's our explicit formula. If we wanted a recursive formula, if you remember, that's the easy one. That's just saying that A sub n is equal to the previous term plus 7. And that's it. So there's your recursive formula. Because D is 7, so you're adding 7 each time. All right, let's jump over here and finish up with geometric. So geometric, our little formula is A sub n is equal to A1 times R to the n minus 1. And so once again, A2 is 3 and A5 is 24. So let's see how this works. A2 is 3, so tell you what, let's do it this way. A5 is 24. Let's put that right there. And that's equal to A1 times R to the 5 minus 1. That is 4. All right, now A2 is 3. So we're going to plug 3 in for A2. And that's going to equal, same thing, A1 times R. But only in this case, our n is 2. So 2 minus 1 is 1. We'll put it there. Now what we're going to do is we're going to do something fancy. We're going to divide the top by the bottom. So 24 divided by 3 is 8. A1 divided by A1 is 1. That's how the A1 gets eliminated. And then R to the fourth divided by R to the first. Well, you may remember that if you have like bases, you subtract the exponent. Or if that's confusing to you, R to the fourth is R times R times R times R. And over R to the first, hey, that kills that, so you end up with R cubed. So R cubed equals 8. R must be 2. 2 times 2 times 2 is 8. So there's R. Now we take that and plug it right back into the easier of the two. So then that's going to be 3 is equal to A1 times 2. Divide by 2, divide by 2. So A1 is 3 halves, or 1.5 if you like decimals. So now we can write our little formula using this guy right here. A sub n is equal to A1, which is 1.5, so I'll leave it as a fraction, times R, which is 2, to the n minus 1. And there is our explicit formula. Sorry for the space. And then the recursive one is going to be A sub n is equal to the previous term times 2. And so there is your recursive formula.